Okay, so thanks. My name is Liz O'Sullivan, and here we go. Not Gavin McWilliams, as is in the programme. And I'm a lecturer with the Centre for Secure Information Technology here at Queen's University Belfast. And I lead the software development in a European project dealing with quantum safe cryptography. So it is widely regarded that significant progress is being made in quantum computing. There are still hurdles to be overcome. However, currently we are regarded to be around this point. This is the 7 steps to fault-tolerant quantum computing. We've made significant developments in this area, and there are still some major hurdles to be overcome. However, it's known that once we get to this stage, that these remaining stages are more of an engineering problem as opposed to a quantum mechanical problem. So we really have the potential of a quantum computer being realized within the next 10 to 20 years or so. There are various estimates around there. Indeed, there are some who are still very skeptical about whether they will materialize. However, in terms of security, we cannot ignore the threat. So, cryptography is the foundation of security. It underpins all of our secure communication infrastructures, and we have to worry about when a quantum computer becomes a reality, because there are certain quantum algorithms that affect significantly or break our current cryptographic systems. So our AES, which is our symmetric key cryptography, and our hash functions are vulnerable to an attack by what is known as Grover's algorithm, and it's a search algorithm. So the effect of quantum computers on these types of algorithms is not as significant as it is on our public key cryptography. What we will have here is a quadratic speedup. So in order to mitigate that, we simply increase or double the sizes of the keys. Here it says AES 256, larger key sizes needed. However, currently the advice is that AES 256 is known or is believed to be safe at present. So if you're being advised that if your system is not at the AES 256, or you're not using SHA-256 or SHA-3 algorithms, then you need to start planning your systems to do so. In terms of our public key cryptography, these will be completely broken. In principle, Shor's algorithm completely breaks all of our current widely used public key cryptography. So that's our RSA, our elliptic curve digital signature algorithm, all elliptic curve cryptography, and our DSAs, our finite field cryptography. So we really have to think of a major upgrade of core technology that we have. These problems rely on integer factorization, or another problem known as discrete log, and these are very closely related problems. So a break in one would directly lead to a break in another. If we take quantum computers out of the picture, it has been widely regarded for a long time with cryptographers is that we have no variability in our public key cryptography. So this is not good. So we have wanted for a long time to have a set of cryptographic algorithms that rely on different underlying hard problems than our current systems. So Shor's algorithm came out around 1994, and ever since there has been The desire to build a quantum factoring machine has intensified, obviously. According to the Snowden reports, the NSA funded an $80 million research program to build a cryptologically useful quantum computer. It is believed that they have made no further progress than the open research. However, in reality, we don't know how far they got. So, in April of 2015, the National Institute of Standards and Technology, NIST, held a workshop on post-quantum or quantum-safe cryptography. And all of the groups from around the world gathered there, and we presented progress within the actual cryptographic constructions themselves, and we discussed challenges going forward in terms of interoperability, adoption within the community, etc. And then in August 2015, the NSA announced that public key cryptography in Suite B, cryptographic Suite B, will be transitioning to quantum safe cryptography. NIST have launched an open competition, and that's how cryptography is developed these days. And the call opened in December 2016. The submission deadline is this November coming, and you should expect candidates to be announced around 2021, 2022. There needs to be a period of around 3 to 5 years of open evaluation and research on these algorithms. In addition to the theoretical candidates, we will require evaluation of hardware and software implementations, investigations into the physical security of the algorithms. And so this will be around our side channel analysis. Typically, particularly for embedded products, our implementations have to undergo a series of cryptographic tests, well, physical tests for physical robustness. So we have a lot of side channel analysis to do here. And then, of course, we have to investigate the embedding of these algorithms into our widely used protocol systems, etc., such as our TLS, our IPsec, and work in this area is already progressing quite well. Google has an implementation in TLS, and the Strong Swan project has an implementation of the Bliss digital signature schemes. What the advice from both from NIST and from the NCC here in the UK is that anybody who has any types of cryptography on their system to prepare their systems for a significant change in core algorithms. However, many organizations that require long-term security, so for example, if they're deploying a system now and the lifetime of that system is perhaps 10 to 20 years, those organizations are already considering this type of technology. It's not ready in terms of a very high security. There's still very much work that we need to do. However, a lot of major organizations, government agencies, etc., and high defense security suppliers are putting this in as a backup technology. So we've probably all heard of D-Wave. D-Wave is an adiabatic annealer, and it's an analog device, and it deals with optimization problems. D-Wave have visited us twice here in Belfast, and this machine is, whilst it can implement Shor's algorithm, it is not really a scalable way to do so. So this is not being considered a threat at present. So what is the cryptographic community doing about this? So currently, the research and the technology is being developed in this area, known as post-quantum cryptography or quantum-safe cryptography, depending on what side of the pond that you're at. And the current leading strategies that we have are code-based. So this is our Macaulay system and Niditra systems. And these mainly only offer encryption. We then have our hash-based technology, so our Merkle tree structures. And here we have the Sphinx scheme and the XMSS, but these only offer us signatures. We have multivariate quadratic, and we know now that these aren't really very practical at present. And the next major scheme or strategy is lattice-based cryptography. There are other kind of methods or methodologies coming out, but they haven't received the amount of attention from the research community that these candidates have had. So we may see more appearing in the future. I lead the software development on this project, which is a Horizon 2020 project. It's called Safe Crypto, and I'll speak a bit more about it throughout the talk. We have chosen to focus on lattice-based cryptography, and there are a number of reasons why we've chosen that. The underlying operations can be implemented very efficiently on embedded devices, and they are amenable to parallelization for GPU systems. They currently go very well onto FPGA devices. And for example, an equivalent design on an FPGA device for RSA and a particular scheme known as the GLP scheme in Lattice demonstrated a speed-up factor of almost 15 times RSA. So they're already very efficient, but there are still some hurdles that we need to overcome in these constructions. One of the very promising areas is that it allows for other constructions and applications beyond encryption and digital signatures. So we all know that we need key exchange for setting up a key establishment process over public IP networks. And we can achieve these with lattice-based cryptography. And an example of this would be the New Hope scheme, and that's in the beta version of the TLS, Google's TLS. We also have these more higher functional cryptographic schemes that are starting to really progress. This is identity-based encryption, and identity-based encryption is not a new scheme. It was proposed by Adi Shamir. For those of you who don't know, Shamir is the S in RSA in 1984, but it was only really solved in terms of the encryption around the early 2000s by Bonet and Franklin. This scheme is an alternative to PKI, so public key infrastructures, and it's particularly attractive for constrained networks because there is savings to be made. There's no certificate that has to be transferred over the wire, etc. So this is being looked at for future IoT networks. Attribute-based encryption allows very, very fine-grained access control. It is an extension of identity-based encryption, and it's been sought for cloud architectures. Currently, most of the security within cloud architectures relies on the type of cryptography that we have today, which was not developed for cloud architectures. So these schemes are very attractive, and they are close to, because IBE is already practical. We don't know the extent of the penetration out in actual markets, but we know of some very high security schemes out there, and they scale well, and they are indeed very suited to constrained networks. ABE is a little less practical at present, but there's a lot of focus being placed on this to try and get this to the realms of practicability. And then, of course, we have our fully homomorphic encryption, which is a cryptographic construction that allows you to compute on encrypted data. So if you do multiplies and adds, etc., it would be the same as if you actually decrypted, completed the operations, and then re-encrypted again. It is currently not practical for most applications, although a sister project in Europe has found certain use case scenarios where this can actually be used, and I believe it's more of a somewhat homomorphic encryption scheme, so it's not the full scheme. So the Safe Crypto project started in 2015, and the goal is to provide a new generation of practical, robust, and physically secure post-quantum solutions. In this scheme, we are developing open source software, so we need all of you to download it and to test it, to try to break it, etc. Because we really will need the help from the community in order to make this a robust library going forward. We're also developing hardware architectures and hardware software co-design. So we're working on cloud architectures with RSA, EMC, but recently now they're Dell. So Dell, or whatever they like to call themselves. They don't quite know what they call themselves these days. And then we're working in the area of satellite communications with Thales. And public safety communications with a UK SME that works a lot for the government on public safety communications, so our emergency services, etc. They are typically not on open networks, on our public IP networks. So this is not going to work in future. The technology here hasn't been able to keep up pace with a lot of the commercial developments. So they're seeking to more and more look to bring in commercial off-the-shelf technology in this area. Okay, so we focus on lattice-based cryptography because we believe it's not only the most practical, but it's also the most versatile. And lattices are is basically a regular arrangement of points in Euclidean space. So fundamental to a lattice is the concept of a basis, and this is a set of n linear independent vectors with integer coefficients. So from that basic concept, we have fundamental hard problems on which most of our, all of our lattice-based cryptography is built upon. So we have the closest vector problem, and that has proven to be NP hard. And we have the shortest vector problem. So in the closest vector problem, you are given an arbitrary lattice and a target vector, not necessarily on the lattice, and you're asked to find the closest vector to that target vector. In the shortest vector problem, you're given an arbitrary lattice, and you're asked to find the shortest vector within the lattice. And for high dimensional lattices, these problems are computationally infeasible. In addition to that, there are the average to worst case hardness proofs, and we don't have that with our RSAs or our discrete logs. We rely on our knowledge of how hard those problems are simply because they have stood the test of time. We have no way of analyzing in a theoretical way how hard these problems are. Also with lattices, there is currently no quantum algorithm known to us today that completely breaks these. There is some research to do with maybe speeding up certain problems within bounds, but there's no fundamental break the way that we would have with Shor's algorithm. And it is incredibly difficult to build new quantum algorithms. That is known in quantum, in physics, and in computer science in general. So the current favored approach and the most practical approach is this concept of learning with errors. And it's actually the ring learning with error that we actually use the most, because this offers us the most efficiency in terms of reduced key sizes and indeed the operations. So I've put the definition there for you. However, how you would really think about this is a noisy linear algebra system. So typically you're given the elements in blue and you're asked to find red. So here we have the noise added in. Now, if this noise was taken out, we could actually easily solve this by using Gaussian elimination. But with the noise, together with the very large dimensions that we have, makes this problem intractable in a computational sense. So the current schemes, and this is only a selection of schemes, there are many, many more schemes out there. So this scheme is is known as Bliss. Typically we use the letters of the actual authors. So this is mainly by Leo Dukas and Vadim Lubashevsky. And this is known as the Bliss digital signature scheme. And this is the one, this is Bliss B. And this is the scheme that you'll find in Strong Swan. We currently have larger public key sizes, secret key size and the signature size. We still would prefer these to be a little bit smaller, but we have very good security proofs with these. In terms of the scheme, however, it does draw upon the n-true problem, for which we've no security proof. For constrained environments, we have the GLP scheme, and this is Tim Ganuzu, who's on our project, and Vadim Lubashevsky, who leads theoretical development in our project. And this has been demonstrated on an 8-bit AVR, or 8-bit microcontrollers, AVX implementations, and it's very good in a constrained environment. For encryption, you are mainly looking at the n-true. The n-true algorithm is already standardized and has been around from the 1990s. However, it has no security proof, and it also has patents attached to it. But we do believe that there might be some relaxation within the patents going forward because of the standardization process that is occurring. So we're hoping that they will release the patents in this area. The ring learning with error is an alternative encryption scheme, and this is the Linder-Pikert scheme. And again, it's very efficient, and this is mainly the one that we are mostly concentrating until we know. So this scheme here and this scheme here are the two schemes that we are mostly concentrating on at the minute. And of course, in terms of key exchange, we have the New Hope scheme. There are others out there, but these seem to be the main ones that people are focusing on. Will these go forward to the competition? Not necessarily. We're currently working on new schemes. For example, there's a hash and sign scheme. This is actually a Fiat-Shamir transform digital signature scheme. So we're also working on hash and sign signature schemes as well. So as yet, we don't really know which ones are going to be submitted to the actual competition. However, the nice thing about lattice-based cryptography is a lot of the underlying components and blocks that go to make up the constructions are the same. So once you have the core blocks built, you can literally you might have to change modulus sizes, certain parameters, etc. And whilst that's easier to say than do, particularly on FPGA devices, once you have those blocks efficiently implemented, you can then construct any other scheme. So the core building blocks in this type of cryptography are, we have our arithmetic blocks, which is polynomial arithmetic. And currently the best way to do that is via this number theoretic transform, which is based on the fast Fourier transform. So it's a multiplication technique, it's a polynomial multiplication technique, and it's particularly suited for large integer multiplication. We do have modular reduction and vector arithmetic. We have our typical logical operations, bit reversals, Hamming weights, endianness, and logs, etc. These are quite lightweight. They don't take up a lot of resources and time. And then, of course, we have our cryptographic, our CSPRNGs, our DRBGs, our deterministic random bit generators. So these are the types of schemes that if you're going for FIPS certifications, you will have to, you wouldn't typically use a CSPRNG, you would have to use a DRBG. So a DRBG has extra functionality built in, such as backtracking resistance, etc., for issues such as per seeding, per randomness, etc. And these are, that can have an effect on the actual the speed and the performance of your implementations. CSPRNGs, for example, are stream ciphers, etc. Our salsa, or cha-cha 20, which is it's the replacement in Google's for RC4 TLS, and of course we have our hashes, etc. So I've deliberately skipped the Gaussian sampling because this obviously plays into this new, relatively new component that we don't see in any, we've encountered modular reductions, maybe not NTTs as much in our traditional, cryptography, but we have this addition in discrete Gaussian sampling. And whilst this has received a lot of attention in the past, this is probably receiving the most research at present in terms of the literature. And indeed, it is a significant component. You're okay. So there has been several suggestions and algorithms developed in the literature, and the type of algorithm that you will choose will obviously depend on your application and your target device. For example, on an FPGA device, and it really does depend on how much block RAM, etc. you have available, but the overall winner, if you want to use that term, would be your cumulative distribution tables. So holding tables within your memory. This, of course, presents issues for those schemes where the table can become quite large, and they usually do. So therefore, the need for extra RAM, block RAM, etc., and off-chip memory is required. But this appears to give us the best in terms of a nice overall balance. Nuthio and Bernoulli perhaps in constrained devices. Bernoulli would be our choice if we were going to an ARM or an 8-bit microcontroller, because there wouldn't be an awful lot of looping in this type of algorithm. So it appears to be the best performing algorithm for that specific target device. We have recently developed a Ziggurat, an embedded Ziggurat implementation. It's not embedded in terms of you can go, there is some ASM instructions coming into it. But if you want a general all-purpose flexible sampler in software, this in our current tests is performing the best at present. So this would looks like to be our, our winner in software. So this would be our winner in hardware, and this would be our winner in constrained devices. New CAO, I still think there has a lot of development to be had there. There are groups in Belgium working on SIMD implementations, etc. So we could see that change in the course of the evaluation period. So just to give you an overview of our current results, typically most of the work is being done at the minute. We're looking at the entire schemes, but a lot of our work has been around these Gaussian samplers. These are not necessarily the most intensive parts of the actual cryptographic constructions, but they are a significant component. So one of the things that we're noticing is what you would expect is that your choice, and sorry, this is not really clear, it was just a cut and paste, but the choice of the underlying source of randomness has a significant effect on the actual sampler that you use. And this in turn affects your encryption scheme or your digital signature scheme. So for example, in this study, we took two AES. So here we're using the Intel AES algorithm, and this is just the standard AES DRBG. We've looked at, this is SHA-256 hash and a SHA-5112 hash DRBG, and then we looked at the Blake hash functions. We've Cha-Cha-20 Salsa for our stream ciphers, and then we took two non-cryptographic safe random number generators. So this is Isaac, and we developed this in a 64-bit implementation of this KISS, Keep It Simple Stupid. This KISS was developed by Marsaglia and Sang along with the Ziggurat sampler. So we thought it would be rude not to implement that one. So here we can see that, that our non-cryptographic, our non-CSPRNGs are showing significant performance. Compared with the likes of your AES and your hash DRBGs, hash in general is not performing well at all for this particular type of functionality. You will use hashes throughout other areas of the constructions, but as a DRBG, it's not considered to be the way forward. And indeed, NIST, when we published this paper, and NIST have since confirmed that if you need to implement a hash or a DRBG, which you do need to for the competition, that the AES DRBG is the preferred method going forward. So if any of you are thinking of submitting to the competition, AES seems to be the way forward here. There are still some arguments going on as to whether, stream ciphers, etc., can be used, but NIST seem to be quite adamant that they would like to benchmark these algorithms using a NIST-approved DRBG. So these, in turn, these results do affect the overall system. The Gaussian sampler is currently not the most resource-intensive operations. Still, our modular reduction and our NTTs are proven to be the most intensive operations. We're currently analyzing these with instruction set extension analyzers, etc. So we're really performing a very deep analysis on where the actual bottlenecks are, so that we know when we're going for hardware software co-design, where we will target our specific instructions in order to be put into these. So, however, a lot of work is going on in improving our NTTs, etc. So whilst currently this may be masked, by the polynomial arithmetic, etc. Once those operations start to be optimized, this is an underlying issue and it will be there. And this is currently the subject of great conversations on the post-quantum forum within NIST of how we actually do this, because this issue of grabbing people when they're designing cryptographic systems, that they almost think that you get random numbers for free, and we don't. We have to think about how we actually get our random numbers, etc. So our main partners in this is Thales, and we have a use case on satellite communications systems, which we're hoping to demonstrate at the ETSI. We're a member of ETSI and the ISO, so we're hoping to demonstrate this to ETSI in September as a fully functional, secure channel for satellite communications. We're working on new approaches to access control systems within cloud-based architectures. And here we're particularly interested in our identity-based encryption in this use case and our public service communication systems. And here we hope to be able to at least not maybe achieve attribute-based encryption, but at least to give estimates as to when or what is needed in order for this technology to be more practical within a lattice-based framework. And that's it. So it's www.safecrypto.eu. Hopefully you'll find a lot of information on it. And please look out for the open source, which should be released next year.
I'd like to open the floor to some questions if we can, anyway. Just put your hand up and bring the mic over.
Just maybe two questions. One, could you compare the key sizes that are expected that we'll have with lattice-based versus what we're using nowadays, say with RSA? Will the public key be a lot bigger, say?
Yeah, so it would be around maybe 2.5 times the size of a 2048-bit. So currently with our Bliss scheme, the public key size, I think, is 7 kilobytes. So they are, they are a bit larger, and we need to be very careful to say, while we're saying that they're much more efficient than RSA and ECC in terms of underlying operation. So we have to think about things like the larger key sizes in terms of, fragmentation, reassembly issues, and bandwidth, etc. So they are.
The question I was going to ask is about perfect forward secrecy in terms of key exchange. Is there any developments on that in the post-quantum world?
So at the minute, actually, the main approach for the key exchange is the CHEM functionality. So in terms of some schemes, the New Hope actually, I believe, does have perfect forward secrecy. It's like a clock arithmetic scheme. So, for example, in our satellite use case, we require that. So one of the schemes that was a key encapsulation mechanism using a long-term key, we couldn't take that scheme forward. But there's a way around it within CHEMS that can actually be done. And there was a scheme by Vadim Lubishevsky, the sum is less than the whole of the parts or something, that we're currently looking at that actually does. And the reason that it does is because of the decryption error, that you can only decrypt at, you have to have that, it's like a threshold problem. So there are schemes that actually do have that. I'm not sure whether NIST are requiring that going forward. I'd have to actually check the list of requirements.
Any other questions?
Okay.
Oh.
So apart from lattice-based, is there anything else
So what I believe is another approach is the hash-based digital signature schemes. They are perhaps an option if you're looking for code signing. That is one of the use case scenarios where that might be an appropriate signature scheme to go for. It's there are issues with it. You're required to keep state, which can be demanding. And so for many applications, it just simply won't be practical. But they are a good option. In terms of the Macaulay signature scheme, there is still, the problem there is that the secure schemes are based on GOPA codes and they are still quite large. So we still have, on any of the attempts to build more efficiency into the schemes have failed so far. So we don't really have a way to go there. So currently, and this is my own opinion, please don't say that this is the opinion of the community, but currently lattice-based gives us the most versatility. And then hash-based for specific instances. So it really will be, and one of the things going forward in the NIST competition is that they won't select just one. They'll give a range. So that you might actually have, so currently we can only achieve key exchange with lattice schemes. So we're likely to see a lattice scheme being selected there. However, in terms of signatures, they may select both a hash scheme and a lattice scheme. So they've definitely said that it will not be just one scheme that you will be required to implement. There will be a range of choices that you can choose, and then they will give guidance on what particular scheme would be suited to what particular application. All right.
So the mathematical problems that our today's algorithms rely on, they are supposed to be hard to solve, but actually there's no formal proof that they actually are. What about these lattice-based encryption? Is there a formal proof that there is no efficient algorithm to compute the basics and
there is.
decrypt?
There is a quantum reduction that was presented in around 2005, I think, by Oded Regev, who's a quantum physicist, works a lot with Daniel Michiancio, etc. And so they, and Vadim Lubishevsky, there is a quantum reduction, so it's a proof of the quantum hardness of lattice-based cryptography. However, we must always remember that there's an awful lot of unknowns with quantum computers. Until we actually have a fully functional, scalable quantum computer, we cannot verify anything, any of the claims for any of the schemes. We can have certain proofs going forward, and we certainly know that there's no way that, in order for us to actually, to break the algorithms, but we, like everything, I don't think we have any proofs per se. And in the same way is that a security proof will not prove that your implementation is secure. It just gives you bounds and tightness and in terms of the analysis that you do. You still have to cover all of the physical robustness, etc., of the actual algorithms themselves. So whilst I say yes, we have a proof, but we must always be careful, and definitely we do need more research in this area. Thank you.